It's a melancholy scene. Here's this cabin. You have no idea what happened, but it's there, and everything in it is the same age, the same vintage. Perhaps 500-600 yards beyond it is a structure that was completed a week ago, or maybe 2 weeks ago. It's of the latest design and is carrying power to probably the most modern of conveniences. Air conditioners, washers and dryers, and here we are. This man had no modern conveniences, no ironers, no washers, no dryers, and we're putting a power line right alongside of him that it would seem that had he been alive and been associated himself with these modern conveniences, he would have had power at his door.
Bonneville Power Administration is building some power lines through Central Oregon, part of the Pacific Northwest, Pacific Southwest Intertie.
There's no line anything in the world like this one. Nowhere.
The biggest transmission program in the United States, these high-voltage lines will eventually tie together utilities in 11 western states, all the way from Vancouver, British Columbia to the Mexican border. The Intertie is composed of 4 big lines running south from dams on the Columbia River. These lines will be able to carry more than 4.5 million kilowatts, twice the output of Grand Coulee Dam. Two of the lines are 500,000-volt alternating current lines, and 2 are 750,000-volt direct current lines. The Bonneville Power Administration, the Bureau of Reclamation, 4 private utilities, and the City of Los Angeles all are building portions of the project. Bonneville is building 3 lines, and part of the 4th, across Central Oregon. They start where the power is generated, at the Columbia River.
People in the power business have been talking about the idea of an intertie on the West Coast for over 30 years.
Well, in the Northwest, we have an excess or surplus amount of water in the summertime because the Columbia River is a glacial stream and the snowpack is melting and the river floods at this time of the year. So we have an excess of power that we could send to the Southwest when they need it for air conditioning and irrigation. In the wintertime, when our rivers are low and when our loads are high because of the cold weather, we need more electricity up here, principally for heating. And if we have a connection, an intertie to the Southwest, we could get power back from them during this winter period when they don't need it. Surplus power from steam plants. The economics of this would come out ahead.
I think it's really a wonderful idea. You help me and I'll help you, and everybody's happy.
Secretary of the Interior Stuart Udall appointed a task force in 1961. The task force had to study the technology that would be used, the benefits that would result. They had to look at the costs, and they had to investigate the feasibility of the entire project. It later recommended that the intertie be built as soon as possible.
But the maximum economic potential of the intertie couldn't be realized until we knew more about long-distance high-voltage transmission, and especially direct current.
or getting any action out there yet?
The direct current technology was new. It hadn't been tried yet in this country, so in 1963, Bonneville built a $2 million test center near the Dalles, Oregon.
Our studies had indicated that there were greater savings, that we could transmit the power cheaper by using DC. Therefore, we tried to catch up on the technology in DC so that we could go ahead and build these other two lines at DC and achieve the greater savings.
Designs were developed, Congress approved, and in 1965 the Intertie project started. From the Columbia River all the way to Los Angeles and Arizona. We're building power lines, of course, and also substations, capacitor stations, and for the DC, the Celilo Converter Station, which changes alternating current to direct current for transmission.
From the Columbia dams, the lines begin to run south toward California.
Most of the material for the lines, the steel, aluminum, insulators, hardware, and wire, is stockpiled in Bonneville's Bend, Oregon construction yard.
It's halfway to the California border, sort of in the middle of things.
The Bend yard is Bonneville's biggest. It supplies most of the construction in Central Oregon.
This is quite a big job in itself because you have thousands of pieces of steel and you've got to know where each and every individual piece is.
The intertie goes together like a giant erector set. The contractor pulls the pieces he needs for assembly in the field. Bonneville's office in Bend coordinates supply and construction.
This is the line that...
It's a fascinating job. Things are changing all the time.
Yeah.
Some of the things make you scratch your head and groan. Oh, that paper. Volumes of paper.
A lot of paper concerns the right-of-way where the towers are being built.
What roads that appear on the map that we figure that we'll use for access, when you go out there with a Jeep, why, run through little swales and there won't be any road at all. It'll just be rocks. But we have to find out how to get there to do the work.
The towers are assembled on the ground, either completely or in sections, to be lifted by a heavy mobile crane.
We have to go up to each section where we stack one section on top of the other. We have to go up and the crane lifts each section and sets it on top of one another, and we bolt it together in the air.
Tolerance are within 1/100th of an inch. That's how close it's got to be. Everything's got to be just plumb and perfect.
Sometimes steel does get mispunched at the factory, and when we have to make fuel adjustments to make it fit. Wham! That's a fuel adjustment. Yeah, you gotta put a little butter on it sometimes.
We're not playing around with the little towers that we see on distribution lines around the country. These structures are big. They're huge. They're massive. They have to sustain tremendous loads. Many of them extend over 100 feet in the air. If you stop to think about 100 feet, this is 10 stories on a building.
Well, you get a good view from the top of the tower.
It just becomes your second home. You get calluses on your overalls, and sitting on the cold steel, we have absolutely no protection up there against the elements. It's always 100 degrees colder in the air than it is on the ground.
Bonneville started putting up these towers in 1966.
They're building the Intertie as fast as they can because each month and each year that goes by just means that more power is wasting into the sea.
Yeah, like they told us when we first started here, they're going to give us a 10-mile start and turn the juice on. We had to stay ahead of it from then on. Huh?
Tower, mile after mile.
And it's about the same thing all the way down the line. Once you do 3 or 4 of them, just like tying your shoes in the morning, one right after another.
Hey, watch out over there! Yeah, catch it, baby!
The first line on the Intertie to be placed in operation was one of the 500 kV AC lines. This went into service in 1967.
We're also building substations and capacitor stations for the AC lines. Substations let us take power off for distribution along the way, or add it to the lines from other systems. Grizzly Substation in Oregon is being built both by Bonneville and by Portland General Electric. Malin Substation near the California border is being constructed by Bonneville, Pacific Power and Light, Portland General Electric, and the Bureau of Reclamation.
There's been a spirit of cooperation all the way through.
Capacitor stations allow us to transmit more power over a long line.
The use of series capacitors compensate for the inductive reactance of the line and in effect make the line look shorter. This way you can transmit a given amount of power for a longer distance or more power for a given distance. It's very difficult to explain in layman's terms.
They're compensation stations, we call them capacitors. Some people call them capacitors, some compensation, they compensate for line loss. It's as simple as that.
The two AC lines are multi-purpose lines. They're used both for moving power down and also reinforcement of the systems in which they interconnect. Now the two DC lines will essentially move power just point to point from the Pacific Northwest direct to the Pacific Southwest and the Hoover Meade area.
The Intertie's direct current lines will be the first high voltage DC lines in the United States and the longest in the world.
This DC line should eliminate a lot of problems, switching problems, line loss. Gee whiz. Looks to me like it would be the thing.
At both ends of the DC line, converter stations are being constructed. Bonneville is building Celilo Converter Station near the Columbia River, and the city of Los Angeles is building the southern terminal station at Sylmar. These stations will change alternating current to direct current for transmission, and then convert it back to 60-cycle alternating current for distribution to consumers.
Well, you see, for many years we've used AC, 60-cycle AC as a standard on the power systems in this country. And this is principally because we can run alternating current through transformers to raise or lower its voltage, and in this way we can reduce it to relatively low voltage, safe voltage for use in homes, or boost it to very high voltage for efficient long-distance power transmission. Actually, power can be transmitted at high voltage DC in a more efficient manner than in AC. But it's only very recently that the technology in DC equipment has progressed to the point where we can get both reliable equipment and equipment that's economically competitive with AC transmission methods.
When the towers are up, we hang the insulators and get ready to pull the transmission wire through.
One of the things that we had to learn was how to properly insulate these lines for this voltage. What the proper spacing was, what the proper number of insulators were, and how these insulators should be designed.
Hold it!
A small cable called a sock line is used to pull the heavy conductor through the towers.
We also needed to know what size conductors should be and their configuration to be in order to keep the corona and the consequent radio noise to a minimum.
About 3 miles of cable are strung at one time. There are pulling machines at one end to pull the wire through the towers, and tension machines at the other end to let it out from the reels. Each reel holds more than 1.5 miles of aluminum conductor.
The cost of a line runs a little over $100,000 a mile.
That's everything. That's land, steel, construction costs, the whole thing. Everything all bunched together. Guts, feathers, and all.
When the whole intertie is finished in 1972, it will have cost $700 million, shared by private utilities, the federal government, and the city of Los Angeles.
If your economy is going to grow, then you have to have more electric energy.
The intertie will result in economies of operation so that the homeowners' rates will be lower than they otherwise would be.
Water will be directed through penstocks to turbines to generate electricity, which will go to California to displace steam generation, instead of it going over the spillways and wasting to the sea.
We've got power to spare when they need it, and they've got generation to spare when we need theirs.
Economically, it's a natural. Just can't be a situation like that.
I've no doubt that the intertie will be strengthened further in future years as the systems to the north and to the south continue to grow.
I think the day will come when there will be DC lines tying the American continent completely in a grid system.
So the snow that is falling today in the Tetons, when the intertie is completed, will supply power into Arizona and even Los Angeles. And that's a fact.